If you have to define me what I am, primarily I'm definitely a theoretical physicist. The rest of the things that I do are in part motivated, in part around that. My competence, if I have any, it's in theoretical physics. I don't like to define myself, even in front of myself. I like to keep things open. And when I started writing books for the large public, there was a moment in which I was telling myself, wait a moment, are you just turning into a writer instead of a scientist? And then I realized that this is a meaningless question. I'm just doing what I'm doing and things are connected. The only meaningful question is how many hours I devote for one and the other. That's maybe it. I have this conviction since a long time. I've been interested in philosophy since I was a kid. When I was a student studying physics, I also continued to study philosophy. And I think that the clear-cut separation is a bit artificial and is damaging for both disciplines. Not all physics needs to talk with philosophy. If you have to solve the Maxwell equations for a certain antenna, you just happily ignore philosophers. And a lot of physics is just concrete, specific problems. But of course, there's a part of physics which is not to apply knowledge that we have for solving problems, is to find out what is the knowledge we have at the basis. And that part, it's a kind of things that, Einstein, Maxwell, or Newton, or Galileo, Boltzmann were doing, or Heisenberg. And that kind of activity traditionally was done by people who were schooled in philosophy. I mean, Einstein had deep knowledge of philosophy, and so Heisenberg and certainly Newton, Galileo, he was an avid reader of Aristotle. There's a mistake in the understanding of physics and science in general. Science is just collecting data and writing equations that predict this data. I mean, that's just a little part of it. The largest part of it is figuring out a set of concept, a conceptual structure, how to think about that. When you go from, the Ptolemaic to the Copernican system, you don't just collect data, you rearrange the order of the world in a different way. That's what Einstein did, that's what Maxwell and Faraday did, that's what Heisenberg did, and Boltzmann and so on. So the core problems in fundamental physics today, like quantum gravity, the problem in which I am, do require the same kind of rethinking the conceptual basis of a discipline. And the philosophers are very good in that. Philosophy has a capacity of critical thinking, which is very deep, has imagination. Philosophers come out with completely different ways of thinking about reality. Sometimes crazy, we don't care about that, but that's not the point. Sometimes very useful because physics is a process, and right now the number of open questions where philosophical thinking, philosophical clarity is useful. Some of them, for instance, have to do with time. In trying to write a quantum theory of gravity, of course, space and time have to change because now we're looking at the quantum property of space and time. We have so many prejudices about how space should be, and how time should be. A careful philosophical analysis of what we know, I find it useful. Even in simple things. One very well-known problem about time is that the past is different from the future. And so what's the root of this difference between past and future? Is that something intrinsic in time by itself or not? And the answer is not just academic. Well, yeah, it is academic. But the question is important because if we want to understand more, to understand how quantum gravity works, we have to get clarity about these things. The nature of the observer is another one. We now are in this funny situation with quantum mechanics, which is a fantastically good theory, but it's formulated in terms of an observer. So why? Do we need a guy with a PhD in physics to understand how the things work? No, I mean, things work by themselves without an observer. So how to make sense of that? And these are questions that physicists have been struggling with, and they will come out with a solution. I think solutions are being debated around the table. Philosophers can listen, contribute, and provide perspective. Reality is not what it seems. It's actually the first popular book that I wrote about science. But I didn't know how to do it. Because how do you tell quantum gravity to people, right? I mean, you have to digest general relativity, you have to digest quantum mechanics. It's a long story. For long, I hesitated because I wanted to do physics and not waste time writing. Then I started considering the idea, but I couldn't find the right way. And then it was a flash. I had so many things to do, but I couldn't organize them. I mentioned in one of the preface of my books, and I don't remember which edition, I was driving from Italy to France, where I had moved at the time, in the middle of the night. And then I said, well, I need to explain this concept. I need to explain this concept. I need to explain this concept. I need to tell the reader what is a field. electric field is not clear. I need to tell a reader what exactly we mean by geometry. It's subtle. I need to tell a reader that particles are not precisely particles, so there's some discreteness, some granularity. And then I started thinking maybe I should say when these ideas were born. So the ideas needed to understand. If I tell how they were born, and suddenly the entire history, the narration came in front of my mind. I just talk about Democritus, I talk about Galileo, I talk about Faraday, I talk about Maxwell, what problem they were addressing, how they come out with that particular solution, and why we're using this notion now, and how this notion built up, changed, and came all the way to quantum gravity. And this is evolution of the world. At the time of in the Renaissance, there's this idea that this is res extensa. Then Newton comes and says, okay, I got the world. It's a space, time passes, and there are some little stones that move around with forces. And then Faraday comes and, wait, you're missing something. There's a field, okay? And Maxwell put order in the field. And then Einstein comes and said, look, the space and the time are actually mixed, a space-time. And then Einstein 10 years later realized that the space-time is a field. Wow. Okay, now we connect the notion of field, and quantum mechanics connect the notion of a particle with a field. So unless you go through the way these things developed, you don't get them. So I decided to write a book without details, but with a core flow of ideas. I think the most fundamental point about learning, the difficulty of learning is not to learn something new. That's easy. The difficulty of learning is to unlearn what we think we know. So we just don't give up easily the ideas we have. And we don't learn unless we give up. I've been reading this summer, because we're doing an audiobook in English, Galileo greatest book. It's the dialogue of the maximum systems of the world. It's a fantastic book. It's a book that convinced humankind, in fact, that the Earth is moving, spinning, and is going around the sun. It has all the argument for the Earth to move, but rereading it, surprise is that the arguments are just a few pages. The large part of the book is to convince the reader that it's possible to question what he gave for granted. It's all about, look, you think that, but that might not be right. It's only when 3/4 into the book, say, okay, now you're open to the book. I haven't argued anything. Only at that point, he brings argument for the movement of the Earth, which, by the way, are wrong argument. But nevertheless, he convinced the world not by giving good argument, in fact, there isn't wrong, but by showing that there's nothing wrong in accepting that something completely obvious to you is it's not right. I think that the idea that, we're missing something crucial, fundamental down there is just wrong. The point is that we have to take seriously what we learn with quantum mechanics and seriously what we learn about generativity and bring them together. And they do go together. I'm a very conservative guy from this perspective. I don't believe we need something new. So I don't see any evidence that we're missing something. Generativity, it's about space-time. So it's a shape of space-time. And that's quantum. And so we have to understand the quantum properties of time and the quantum property of space. That's radical. So the assumption is conservative, but if you follow up, this is completely radical, because it means it's a continuous space that you thought was, forget about it. The time evolution in a single variable, forget about it. You have to replace the usual way of thinking space, the usual way of thinking time, with something consistent with quantum mechanics, but not this quantum mechanics in space-time, of space-time. So for instance, you have to have a mathematics and a physical intuition that allows you for having quantum superposition of space-times, plural. Like there is a Schrödinger cat that can be both awake and sleep, or somebody said dead and alive. And so in the same sense, space can have a shape and also another shape in a superposition of the two. Suppose loop quantum gravity is confirmed. With a colleague, Marius Christodoulou, we have an experiment which we proposed, which might even be doable in 10 years or so, which would actually test the discreteness of time predicted by loop quantum gravity. Like light is made by photons, space is made this grain of space, but also time. I expect it has this granularity. We have an idea of perhaps with some slight advance in technology, not excessive, could be tested. Now suppose this come out right. Loop quantum gravity is correct. Perfect. The right numbers are there. Now what? We still have a universe described by a funny standard model where the weak interaction and the strong interactions are completely separated, described by similar theories but not really unified in any way. Gravity described by still another theory. 19 parameters of the standard model with who chose them, why, 3 generations. Suppose with quantum gravity we figure out the Big Bang, and what seems likely is that it was not the initial explosion, it was a bounce. I think it's a reasonable hypothesis. It seems to be more reasonable than the Big Bang. Suppose we figure this out. Have we solved everything? No, of course. I mean, what was the collapsing universe coming from? It seems today so impossibly difficult to figure out what was in the collapsing universe. But at the time of my grandfather, it seemed impossible to discover what was the chemical composition of Jupiter. Science finds new problems and grows at all levels. If the mystery is not a reason of sadness, it's a reason of joy because there are new things to discover. It's the beauty of understanding.